very lot, like the attendance is quite low. I was expecting at least 30 people. Did you guys not enjoy like lot the things we discussed last time? Was there any confusion? Hello? Please at least type in this message box. Thanks. I'm expecting a few more people by 6:10. Then we'll start. Okay. Yeah, students are playing outside, so I can't do anything. I'm shouting a lot. A lot of new people have joined today, which didn't join last time. Okay, so yeah, let's start. I can increase the font. Is it visible now? Cool. So this is our last notebook. We'll be looking at some other things today. So yeah, hello everyone. Let's start the session. This will be again a doubt session as well as a discussion session that will revolve around discussing the doubts you might have faced in week 1 and week 2. Not week 3. Week 3 we'll be discussing next week. Okay. And apart from that, we'll also see some of the coding problems and network X, like how to use network X to basically visualize the graphs. Last time we discussed how to build the graphs. Today we'll be discussing how to visualize the graphs. Okay. So I'll see a lot of new faces here. Please, the new people, can you introduce yourselves? Those who didn't join in the last session. Hi. Yes, yes. Okay. So what do you do, Krishna? Okay. Okay, okay, great, awesome. Where do you study? Okay, okay, great. Yes, yes, I know. So you're in BTech, right? Okay, 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 great. So yeah, anybody else who wants to introduce themselves? Yeah, hi, hi. One by one, please. Okay, hi. Okay. Thanks a lot. Uh, Anybody else? Hi, Samuel. Hello. Okay, okay. Great, great. Good, great. Awesome. Sarthak? Hi, Sarthak. Okay, great. Uh, okay, okay. Awesome, awesome. Anybody else who wants to go? Hi. Okay, okay. Great, great. So I won't be going a lot into introductions right now because we have a lot of things to cover. Last time we fell short on time to discuss a lot of things. So yeah, first of all, I'll be discussing the doubts of week one and week two. If you have watched the videos, if you have any doubts, please go ahead. Okay, I'll be taking the doubts one by one. Please raise your hand, and then I'll be taking the doubt. Okay. Any doubts, guys? Any doubts? Simple, basic, like what is social network? These sorts of doubts will also be taken care of. Okay. No doubts. How many of you have done assignment one? Have you submitted the assignment one? I mean, it's very basic still. Great, great, awesome. Great. So I don't think so you guys would be having any doubts because the assignments are very simple. Like first two assignments were very simple. I hope you guys have scored everything like full marks, 100%, huh? So yeah, since you guys don't have any doubts, I want to discuss some things, not just the network X part. Let's solve some. Let's some study some basic things in social network analysis. Okay. Let me connect my iPad. People are still joining. Okay. There's some issue with the iPad right now. Let me first of all, let me discuss some of the questions from the book of Professor Tanmay. So I will go chapter wise. The chapter one is basically the week one. Okay, and I will be solving some of the basic questions which are given in the book. I will be writing them here. I will be typing them here. Just give me a second, guys. I need to check if this iPad can get connected. Okay. Um, so I hope you guys are able to see my iPad screen. Okay, is it visible? Great. So the first question, I will solve some objective questions first. For till 6:45, we'll be solving these questions from the book, and after that, we will start with network X visualization. It won't take a long time because the visualizations are quite simple. We just need to uh, play with hyperparameters of the functions of the classes to see how the those things affect the visualizations. Okay. So first of all, the objective type question. So say you are given a graph G, V comma E with V vertices and E edges. So what is the time complexity of what is find time complexity of adding and removing a node in G. Can you guys solve it? I'll give 2 minutes, okay? Can you guys solve it and give me the answer? What is the time complexity of adding and removing a node from this graph, in this graph and from this graph, okay? Shall I give you an option? Like all the options, okay? So O1 O V square O V square and O1 O1 and O V square. What is the correct answer? No answer. So let me discuss. Okay. So we have discussed two techniques. Okay. To represent a graph, one is adjacency matrix, and other is adjacency list. These two things can represent a graph easily. Correct? Okay, Sarthak has given us an answer. The answer is D, for adding its O1 and for removing its OV square. Okay. Anybody else? Sarthak, can you tell us how did you come up with the answer? Okay. Okay. Can you can you solve how did you solve, like mathematically, not just visually? Visually you can simply, like intuitively we can find an edge simply by looking at the graph, but mathematically we have adjacency matrix, correct? So how do you remove an edge or add an edge in adjacency matrix? Mm-hmm. 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 Okay, just let me tell you. Okay, so say we have four nodes in a graph. Hmm? There are four nodes in a graph, say A, B, C, D. A, B, C, D. A is say C is connected to A. Let me just make this A, B, C, D. C is connected to A, 1. C is connected to D, 1. Okay. Then since this is an undirected graph, so here also C is connected to A, C is connected to D. This will be symmetrical. Okay. The matrix will be symmetrical. And then B is connected to C. B is connected to C. B is connected to D. Okay, so how would B be connected to D? B is connected to D and B is connected to D. So B is connected to D. Now if I want to remove node, say I want to remove I want to remove node C. So what will I do? Hmm? I have to remove the entries. I have to remove the entries where C is 1. Okay, correct. Remove row C. I can remove row C, then I have to remove column C as well. If I remove this, then I have to remove this as well. Sorry, this is I connected B. Let me remove this. Okay. C is connected to D, na? Okay. Yeah, just wait a second. Wait a second. Yeah, we can update the cell, but the thing is, how do we update it computationally? We have to run loops, correct? So that's what we need to discuss. Like how do we go to that cell? Okay, how do we go to that? Sorry, how do we go to that cell? How do we remove the entries from that cell? So C is connected to D. So C is connected to D. Where is D? Here is D. Shit. Then C is connected to D here. Okay. So C is basically connected to A and D. B is connected to uh, just a second, guys. I made mistakes here. C is connected to A, correct? Tell me this adjacency matrix is correct or not. It's correct, I guess. It's correct, right? Okay. So yeah, let's start. Okay. So whenever we want to remove node C, okay, what we can do is there are two ways. We can remove node C from this matrix completely. What we can do is we can run a loop, two separate loops. Okay. So say there's for loop for row I. This is for rows rows A to D, and when row is double equals to C, we delete it. How do we delete it? We basically map all the entries from C or whatever we do. Like there are multiple ways to do it. Then we do it again for column. For column A to D, column is double equals to D, we delete it. But this deletion operation again requires us to run a loop. Okay, correct? So the complexity is of deletion is V square. For number of vertex we are running it twice, loop within loop. So if we come to row C, we have to basically map this entry here, this entry here. Okay, this is one way. This is not a feasible way. This is one way, because then we have to map every entry from below to above. But what we can do is we can make these entries 0. So node C is detached. Node C is detached. It's not removed from the graph. It is existing inside the graph, but there are no edge connections. So it won't be participating in any of the computation of say node connection, link connections or anything. Okay. So this way we can remove the node. Correct. Similarly, we have to run it for this thing for column again. So this thing, this thing. So this is a nested for loop 2 times. This is a nested for loop. The complexity of deletion is V square. Now what is the complexity of addition? So say this is not existing. This node C, we have to add it. Okay. What we can do is, say node C is there, and we know that node C is connected to node B. Okay. So what do we do here? What do we do exactly? The adjacency matrix, in mathematics you can replicate it. Like in mathematics you can say you can use half the matrix, but in computer while coding it, what we have to do is we have to basically perform all the operations on both parts of the matrix, the upper triangular and lower triangular. Okay. Either you can just put the values in lower triangular and then copy the matrix in upper triangular. That will also require the same computation as basically writing the values twice. So what we will do is we will, if the node is not existing in the matrix, say node C is not existing, so we will add another row, another column to the matrix, and we will put values here twice, 2 times. So this thing again we have to do. We have to basically go to that row, go to that column, and then we have to add value. It will be done just once, and it will be done. Sorry, for row wise operations. Say we want to add values. Say C is connected to B. So what we do is we go to column row C, then we go to B, we add 1. Okay. Then what we do is for row again we do. Okay. We go to C, then we go to B, we add 1 here. Okay, so the complexity for both of the cases is V square in case of adjacency matrix. Now the question for you is, you guys, is you have to perform the same operation for adjacency list. Okay, not today, not today. Just note down this question. I will upload the PDF of this on Google Drive. I will share it with you. You have to show the same thing, the same operation. You have to show how do we do it in case of adjacency list and what is the complexity. Okay, so you guys have to solve this question and we will discuss this question in the next class. Great. Any doubts? Cool. Great, great. These are very basic questions, so I'm just discussing them in detail so that the people who don't know, like who haven't gone through or who have confusion in adjacency matrix and this stuff, they can understand it easily. Because in NPTEL videos, the PPTs keep on moving, so we don't get enough intuition how these things work. So that's why I'm going programmatically and how to do it, how to visually, how to dry run programming things using maths here. Okay. So space complexity of adjacency matrix is still like say V square because we are storing V cross V. Okay. Yeah, so this is basic from chapter 1. There are not a lot of questions. So just a second, I need to see some questions to find. So there's a question, short answer question. So let us assume there's a network G1. G1 is a network. Okay. That presents social interaction. This is a social interaction network. Okay. And the size of this network is 6. And say say there is say there's a contagion disease that starts spreading in this network. Okay. So you are a healthcare worker. Say so. What would be the order of vaccination? Okay, you have to solve this question using adjacency matrix again. What will be the order of vaccination? Consider only this. Okay, so anybody, please raise your hand, unmute yourself and tell me like how would you solve using adjacency matrix? We don't want to apply complex algorithms, we just want to see using adjacency matrix what community, what person in this community should we start vaccinating from start, like what person should be the first person? Anyone, please. I'm gonna ask them randomly. Okay, who's joining now? Ashwin, are you there? Hello. Anybody, please, like, give vague answers. We are here to discuss. Okay. What would be the order of vaccination? Big delta value of G. No, no, no. Okay. The node with highest centrality. Okay. We are not going with delta values. These are like complex. Like from adjacency matrix, how would we determine the centrality? Ashwin, from adjacency matrix, how do we find the centrality of a node? You are running for loop. Okay, you have some basic Python packages installed. You have to perform. Say this question is coming in. Say data structures algorithms. What is the first person you want to? Yes, correct. So rows with most ones will be most central. Correct, correct, great, awesome. So you want to, if you want to stop the infection, you want to vaccinate the person who is most social out of that. So the person who has the high central measure, centrality measure, the who has the highest degree will be the person who has the highest number of ones in the adjacency matrix. Say node C is there, it is connected to every node. It is connected to every node. So we will perform count. When we perform count on each row and we vaccinate that person. Then we go to the second highest, okay? The person with highest degree slash count. Then we go in decreasing order. To vaccinate. Great. Okay, so we have another question. So I'm gonna make a network, okay? I'm gonna make a graph. Guys, please don't leave meeting, but we have to study network X again, okay? At 6:45 we'll be starting network X. Um, yeah, this is almost correct. Let me complete it fast. Hmm. Yes, okay. So you have been given a graph that has 7 nodes. And these 7 nodes are basically 7 papers that are published. Okay. So is this network a valid citation network or not? Is this a valid citation network or not? Can we discuss, like, do you guys know what is a citation network? Yes, it could be. It could be. Let's first see why it could not be a citation network. Okay. Can you give some reasons? Can there be a paper? Say there is a hypothetical scenario. There is a parallel universe. where we can publish papers without citing any other paper. Can there be a possibility? Can we publish a paper? No, na. We cannot publish a paper without citing. We have to write introduction. We have to basically write introduction. Okay. We have to write related work. Most of the times we have to compare with baselines. So anyhow, you have to cite something. Is there a node? Can you see a node which does not cite any paper? By the way, this direction means cites. Okay, A cites B. So this means B gets cited by A. So what can you say? Is this still a citation network? Is this citation network still valid? Anyone? I will then start picking up people randomly, okay? Yash, are you there? Hello, Yash. Correct. So, see, this Note 7 is not citing anything. And if a paper does not cite anything, it cannot be a paper. It can be basically a magazine article or something, but still we cannot cite a magazine article. So if these two notes are citing it, it is a paper. It is a published paper. Possibility which is not connected to graph. There is a possibility. There is a possibility. Okay, we discussed this in discussed that stuff in last doubt session. There is a possibility that nodes can exist in a graph, okay, but they are not connected. But in citation network, there can be a possibility that that node exists in a graph, but the no that node or that paper is not cited by any of the paper in that graph, and that paper is not citing any of the paper in that graph, but it is citing other papers which are not inside that graph. But if we combine say a universal graph, okay, the all the papers which have been published on Earth from the start till now, then there cannot be any node, okay, which does not have any edge. There will exist an edge. Otherwise, that paper is not published paper. It will be some article or something. So that paper, say this node 8 is existing, and this is our system. This is our system, but 8 is citing other papers outside the setup, and 8 is being cited by other papers as well, okay, but they are not in our consideration right now. So in this graph 8 does not exist. Sorry, citations and the references of 8 does not exist, okay. So that's why this thing can exist and this thing can also exist. But what did I say is, consider this a complete setup, okay, consider this a complete setup. So given the Sarthak's point, there can be a node, so it might be citing some of the papers outside, okay, but we are not considering this setup. So if this complete setup is considered full, okay, this is a complete system. So 7 cannot just be published without referencing, without citing anything. So this is not a valid citation network. Any doubts? We can say this. We have to this, like, this is in case of citation network. We are given a citation network, then it is assumed that it is complete, okay. The papers which it cites is complete, are inside that system. The papers which cite that paper is inside that system, so that is considered complete, okay. So a citation network, this scenario is generally not possible. Okay, this is not considered in real world cases. You only put up a paper inside a citation network when it is citing someone and when it gets cited by someone. Okay, so that is the case. So there is a website, Connected Papers. Connected Papers always shows you the similar papers. If you search a paper in Connected Papers, let me show you. Okay, say Connected Papers. I open it. This is a very beautiful visualization website. You guys should visit it if you are doing research. Consider I search a paper taxo complete. Okay, let me open it. See what you said, na? These two are disconnected components. Okay, they are disconnected or not? They are not disconnected. There exists an edge. Okay, so this this is a highly this paper. This paper is the one which searched for. Okay, any message? Oh, sorry. Uh, just a second. Visible? See this, okay? If it's visible, it's visible, right? Still no. Okay. Now? Great. Now is it visible? Sriram, Yash, not the graph. Okay, graph is visible. Graph, see the graph. Okay. So this hypothetical scenario which Sarthak asked, uh, the graph, the node can exist in a setup, but generally convention which we follow, the convention which we follow does not say that a node on graph paper should exist in a citation network that is not cited by any of the nodes inside that network, and that is not citing any of the nodes. Okay, so see this, even this paper, this is very less, like it is very far. It is these distances show how relevant the paper is. It is very far, but it is also citing, so somehow it is also citing this paper somehow. Okay, in one way or the other, it is citing this paper, they are citing this paper, so somehow they are connected at all. Okay, let me share my screen again. Mhm. So yeah, these are the basics. These are the basics of how we can represent a social network. Um, how we can represent a social network. Say citation network is there. So this scenario can exist, but not preferred. So that is the answer to the question. Our own citations, paper citation. Um, you can use this website, connectedpapers.com. Is not just citations. You will also find the relevant papers to your paper. Okay, great. So yeah, these are the basics of week one. Week two we will discuss next week, when we will discuss the assignment of week one as well. And we are like keeping one backlog, just so that you people are like, there's a lot of time to complete assignments. So there might be some people who have not started lectures, they might have not finished it. So we are just keeping 1 week backlog. Okay. So coming to network X. Okay, I'm stopping the iPad screen. Um, is my PC screen visible right now? PC screen is visible? Great. So last time what we discussed in Network X, how to read a text file, okay, how to read the lines of text file, because these lines are usually used to represent the edges. Then we discussed how to add edges to a graph, how to add edges with attributes, okay, how to remove edges, how to visualize them. Visualize means the attribute view, okay. So today what we are going to discuss is, this stuff. What do we say? Visualization of edges, visualization of graph. Just a second. Wait a second. I need to do this. Correct. Okay. So I will add text cell here. Visualizing networks. So let us first see some of the basic networks, the basic data which exists inside Network X. There are some graphs, some most common graphs like Karate Club graph. Okay, how many of you know Karate Club graph? You might have studied it in lectures. Okay, how many of you know that graph? Anyone? Karate Club graph? Okay. Karate Club graph. So this is Zachari's Karate Club graph. It basically shows, let's study, okay? Let's not just assume what it shows. Let's study. It's a social network of University Karate Club described in paper, an information flow model for conflict and fusion in small groups. So you can see there are three communities, major communities. One is this major community, the other is this major community. Then inside that, this is one small community. Okay. So this is one of the network structure that exists, that is saved, that is exists as a class inside Network X. The network captures 34 members of Karate Club, documenting links between pairs of members who interacted outside the club. During the study, a conflict arose between the administrator John A and instructor Mr. He, pseudonyms, which led to split of club into two. Half of the members formed a new club around Mr. He. Members from the other part found a new instructor and gave up karate. Okay. So yeah, let's see this network. How does it? How can we visualize it, and how can we separate these two communities, these two group of people who fought? And I don't know whether they won or not. Network X Karate Club. Let me search it. So we found this. Okay. So just copy paste. Okay. Whenever you are writing code of any library or something, don't worry about what you have to remember. You have to remember nothing. You have to just use these functions. Okay. So let me first import. Just a second. Let it get connected. Any doubts till now? Any question? Anything? Share the link. Okay, I will share the links. Sorry. Any doubts till now? Write yes, no in chat, please. No doubts? Okay. So let's see what it's doing. I have made a lot of empty cells. Removing these. So we imported this matplotlib, and this matplotlib library. How many of you do not know matplotlib library? How many of you have not used it till now? You all have used matplotlib. Great. So this matplotlib library is used for. I have you. Yes, you obviously have used. I'm asking other people. Great, great, great. So you know now, like the purpose of it. It is used to visualize data. Simple one-line answer. I'm importing networkx as nx. I'm importing matplotlib. Then pyplot sub. This is a sub function sub library inside it. I'm importing it as plt. Then I'm using this. I'm creating a graph G from networkx, that is karate club graph. Okay, somebody has joined. So then I'm printing, okay. So node 0 has degree 16, node 1 has degree 9. What is the highest degree here? The highest degree is 17. Node 33 has degree 17 and node 0 has degree 16. So I guess these two people fought, and like these two were the leader of their corresponding groups, and they fought and they got separated. So yeah, let's visualize it. I'm removing this visualization part from here. Okay, I will add it here. Okay. Mm. So this is very basic, which we copied. This graph is circular graph. Okay, with labels. Labels means this 7, 8, 9, 1, 2, 3. This is getting added. But can we infer something out of this graph? Are you able to visualize which two people fought, which two groups won, what two communities are existing here? The visualization is very hard. Like from the degree, we have seen 0 and 33. They are highest degree graphs, and we can see here as well. But we only inferred that because we saw that degree there, and that's why we are able to see these two are close and they have high degree. Otherwise, nothing is visible, nothing relevant, and we cannot make anything out of this graph. Okay, so let's check how we can improve these visualizations. Okay, so networkx visualize graph. Coming to this tutorial, basics. We are going back to the basics. Okay, like we studied in last class. Any doubts till now? Okay, no doubts. So yes, let's draw the graphs. There is one very these are the functions which we used to visualize the graphs. Okay, so what we'll do is we will visit them one by one. So there is this function networkx.draw. Draw the graph with matplotlib. That's why we have imported matplotlib. Okay, no edges, no labels, and using full matplotlib figure area, no axis. Great. Let me draw it. Mm-hmm. See, is it possible to identify the YouTube comment, user, node, influencer detection? We will discuss this later. Okay, let me finish this thing first. We are short on time. We have to visualize a lot of things. Okay, I will discuss this after we finish this at 7:50 or something. Okay. So this networkx.draw. Okay, this is also drawing the graph. This is also showing the graph. But still, like this circular has given us nothing. This thing has given us nothing. We can see like 0 has a lot of degree just because it got separated from these nodes. But we cannot make out whether 33 or 32, which one has the highest degree, or 23, which one has the highest degree. Still, this is very confusing. Okay, so let me just these examples. Let's try out these examples. Let's try this. Sorry, this is nothing. Let's go back here, and we saw draw. We saw networkx.draw. Draw networkx. Okay. So these two functions, are almost similar, and they are created. So there you will find very little difference. Let's see what's the difference. Okay, so it is given, the graph is given, the position is given, the axis is given, and these keywords are given. Similarly, here also keywords are given. These keywords can be anything, like what the keyword which we are using is with labels. Okay, so these keywords are generally common between these two. And see, this draw is using the same keywords as network x dot draw network x. Okay, so these two are basically the same function. So this one draws the nodes. Okay, let's try drawing nodes, just nodes. Okay, we can give node color, we can give node shape. Okay, CMap, these settings are of matplotlib. The edge color, these things we can give everything here. So let's try drawing node. Okay, we did some nodes. Okay, it's nodes. So see, network x dot nodes has no keyword arguments. Keyword arguments are arguments which can be passed with which exist, but they are not in function definition. Okay, they are in function definition, but they are written here. There is no keyword argument for with label. Okay, so there is a keyword argument, say simple keyword argument label here. You can see this is not a keyword argument. This is just a function argument label. It is missing argument position. Okay, so let's draw position. What is position? It's a dictionary with node as keys and position as values. Position should be sequential of length 2. So this is basically this function. This function is basically drawing based on 2D coordinates given by the user. This is to manually draw the nodes on a piece of plot. Say you give 0 0 to 0 node, so 0 0 0 will be drawn, 0 node will be drawn here at 0 0. You give 100 comma 100 here for node 9, so node 9 will be drawn here. So this is manual, basically manual drawing. But can you basically give coordinates for every node and node existing inside the graph? We cannot. Like there are millions of nodes in graphs, so you cannot do that. So these functions are for basic visualizations, but they are not of our use. Okay, so these labels, these three functions, they are very basic functions. Okay, they are just to draw edges, labels, nodes at positions which exist inside the graph manually. So we have seen this circular graph. Let me check what arguments we can give. We can give all the arguments which exist in draw network X. So circular graph only draws the graph as circular manner. Okay, where all the nodes exist on the circumference of ellipse or circle or say some other circular structure, oval, and the nodes are connected in between. Okay, so this we have studied. Now next thing is this one. Okay, so I don't think so you have studied force directed layout and this stuff. Okay, have you guys studied this stuff? Force directed layout and spring layout, spectral layout. These things will come later in the course, I guess, or they might not come, but these things are very simple. So basically this force directed exists. Say you have a spring setup. Okay, you have a spring setup. So what you do is where's the graph? I wanted to know about spring. Yeah, I'm telling. Okay, but the basic intuition I will tell, and later things I will share a link. Okay, I will share a link. You can study there. The basic intuition I will tell. So say you are given these many nodes. These many nodes you have been given. Now what I want to do is I'm given these many nodes. I'm given 33 nodes. I know this node gets connected to that node. So what I'll do is I will take springs. Okay, the springs, their tension is same. All springs tension is same, but The thing is, the spring, that spring should, there the count of spring should be the count of number of edges, and you replace that edge with a spring. You connect the nodes. Okay. So what's happening is node A is pulling node B. Sorry, node A and node B are connected. Then node C is pulling node B, and node A is pulling node B. So when you connect everything with a spring inside a graph, sorry, the whole graph, when you connect it with springs, then at stable condition, what exactly, what is the structure of that graph? That is what force directed spring layout and this stuff means. Okay. So these all things, draw spring also, draw spring also. The spring layout is basically the similar thing. Force directed means the stable force. Okay, if you basically connect them with gravitational force or spring force, anything. So these all plots, the spring layout is there, this is the force directed layout. These all things similarly represent one thing. What is the stable equilibrium visualization of that graph? So let's try this out. Okay, let's first try this Kamada Kawai graph, Kamada Kawai layout. Okay, with labels, we can always put the arguments of draw network X thing. Okay, this is not working. Let's remove it. Let's try now. Pose. It also requires pose fit. Oh, sorry, my bad. My bad. Okay, draw with labels equals to. Okay, so this Kamada Kawai layout, it's giving us a stable graph, which means the nodes which have high degree, they tend to be close. They tend to be closer compared to the nodes which have low degrees. Okay, so 16 has degree 2, 11 has degree 1. They always get very far from the nodes which have high degrees. So node 0 is in center, node 33 is in center. Okay, so there's also a randomness associated with these visualizations. If I do it again and again, you will find it same. But because there's a random seed also as well. This not given here. Okay, we will see that later. Okay, so now let's draw this spring layout. Okay, this spring layout and this Kamada Kawai, you will not. Just a second. See, node 16 here, it's very far. Node 16 very far. Node 12, where's node 12? Can you see node 12? Node 12, it's in between. Okay, it's coming to be here. So you see this randomness, this is not very random as well. So but still you can see this node 8, node 0 and node 33. Okay, so high degree nodes, very high degree nodes, they have gone very far with their own community, and low degree nodes are forming around that community. So this is the basic visualization. Hope it can help in maximum planar. Sorry Sriram, I didn't get you. Can you unmute yourself and ask? Sriram, hello? I'm unable to unmute. Okay, leave it. So, yeah, it is basically that thing. Hope it can help it maximum planar. I didn't get you. Can you type it? So intersections, like the intersections, or say, yeah, please speak. So yeah, okay, let me just continue. Okay, so the intersections are there. Okay, you can see this does not exist in 2D plane. These things exist in 3D plane back. Okay, they are projected to 2D plane. So that's what we can see here. Okay, that's why the visualizations change whenever we change the plane. So what it is giving us, it is basically performing principal component analysis type of thing, so that the variance is maximized, so that we can see the maximum graph with separation. It's not if we visualize it from this, we are visualizing it from this plane. If we visualize it from this plane, this graph would be constricted to this much view, and we will not be able to visualize the difference. Yes, yes. Okay. Hmm. No, no, no. There's. I'm getting. Yeah, yeah. Correct. Simple visualizations. Say these visualizations, they do not help a lot in that thing. Okay. So this spring layout, these layouts, they were created back in the day when there was a need to visualize the graphs. The planarity and these stuff came later on in the day, but they were not created in a way to visualize the graph, so that's why if you use this what is what package what library there's a tool, network visualization visualization tools, Gephi. Okay, have you guys used Gephi? Gephi, Jeffy, whatever you pronounce it. No. So I suggest Sriram, please use this tool, and everyone, not just Sriram. Okay, use this tool. So what it tells, it will give you spring layout. It will give you force layout. You can experiment a lot of things here. It gives the graphs in 3D as well, so you can rotate them. You can rotate in any direction. So there are non-planar graphs, and they need to be visualized. So this network X does not give this. This basically takes the maximum variance part, and it then gives us the graph. Had it given it the graph from this axis instead of this axis, this plane, the graph instead of being this large would have been this much. So we would not be clearly visualizing the graph. Okay. So this network X does whatever Gephi does, but Gephi gives you 3D perspective. So you can rotate, you can do anything with that graph. So that I hope that will solve your doubt about non-planar visualizations. Okay. So yeah, we have studied spring layout. Let's see spectral layout. What does this spectral layout do? And there's a lot of stuff in visualization. Say you can spectral. See, nothing. Okay. So these graphs basically, this network X library, this performs very basic visualization. Okay. So whenever you do spring layout visualization and this stuff in Gephi, you can tweak the hyperparameters very easily, and you can see the visualizations changing. Okay. This one, these plots are with default setting, and what's the problem with default setting is we do not get the optimal visualization. So that's why I suggest you guys try out this Gephi tool, and in next class we will take 15-20 minutes to visualize all the types of graphs layouts which exist. There's force layout, there's spring layout, there are other, say there's some people, the layouts are named after some people as well, so I can't remember the name exactly. uh, we will visualize those graphs as well. Okay. So what does a spectral do? Yeah, let's see. spectral 2D layout. What is spectral 2D layout? Let's search spectral layout. Eigenvectors such as Laplace matrix, Cartesian coordinates, blah blah blah. A lot of mathematics behind these things, but the spectral layout generally looks like this only. Okay, so since this zero node is connected to a lot of nodes, this has the highest degree here. Okay, then node 33, where's node 33? It exists here. So basically it converts it in the same shape of a star type of thing, the spectral thing. Like center is there, then all other nodes are pointed in other directions. This is very basic of spectral layout, and I want you guys to try out Gephi, please. I don't have it installed right now. I will install it and I will show you so how this Gephi works exactly. And till then you can try, you can play on, you can download any dataset, you can use default datasets, and you can see how changing those hyperparameters there, you can change the visualization of spectral layout. Okay. And yeah, this is spectral layout. Then we have studied spring layout. Let's draw planar graph. Okay. G is not planar. Okay. So I hope you got. I will tell you. Draw shell. Okay. So I hope you got your doubt cleared, Sriram. So why we cannot draw this graph? Because this is not a planar graph. There are a lot of intersections. This means the yeah, that's yes. That's what this spring layout, this force layout they do. So what they do is basically they create the graph and then they project it with on the plane which has highest variance. So this thing cannot project. This cannot draw it. So let's move to another layout. Say shell layout. Mhm. It's coming up. It's coming up. See, can you notice the difference between circular layout and shell layout? It's nothing. They are basically the same. These functions were created back in the day when they were creating variants of the graph. So circular layout is there. So somebody named that layout and say I will call it shell layout. I will not name it circular layout. So they proposed it and say FML shell layout versus circular layout. This gives nothing. They are basically the same thing. Okay. If I see this function here, so this shell layout, it positions in concentric circles. I will know. Say I will create a dimension. Just a second. Dimension equals to 2. Let's try out this thing. Okay. This seems interesting. And center equals to 0. Center E. Okay, so basically we have to this is center is basically the coordinate. Okay, so if I make it 0, 0, So still, I don't know how they have map 0 comma 0 or something. Coordinate pair around which to center the layout. Yeah, please, what's your doubt? Okay, let me show you circular layout. Can you see any difference? Apart from rotation, can you see any difference? So basically, we can pass the list of nodes for each shell. We can create multiple shells, concentric circles. See, this circular layout, it does not contain, its scaling is there, dimension is there, but it cannot create shells. This shell layout creates shells. Let me create shell, okay? So let's create n list, mode of node lists, okay? Let's remove it. N list equals to, so say 0, 1, 2, 3, 4, 5, 6 are here, comma. 7, 8, 9, 10, 11. It won't run because it's saying node 12 has no position because we have not passed node 12. So let's create it. Okay. Twelve, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 26, 27, 28. My face is coming up. Wait. 29, 30, 31, 32, 33. See? Can you see shells here? Are they visible? So this is what shell layout can do. This is the thing which circular layout cannot do. Circular layout basically draws everything on the radius of a circle that has a fixed radius, and this can draw shells in a concentric manner. Okay. Yes. Got it? We need to discuss some other layouts. Random layout is there. Nothing so special about it. It just draws random layout, as the name suggests. Let's try it. Copy something. See randomness. Okay, I'll run it 2-3 times. You will see the difference, and then we will see. See randomly. This basically draws the graph randomly. So don't expect some scientific reason behind these functions. They were created based on the visualization, or basically the drawings, or whatever whatever the experts created back in the day. So yeah, that's all about the visualization. Then there are other visualizations which I suggest you guys experiment on Gephi, okay? And these visualizations exist in GraphViz, okay? In GraphViz library. Open it. Let's open it. GraphViz is open source visualization software. And what sort of visualizations are available with it? Let's see. So these all are layout engines. Okay, you can basically create graphs with one node in center, other around it. Then there are 2 pi. This is radial layout. You can experiment all these things, and I seriously suggest you guys try these things first. Then we will discuss. Okay. Visualize these websites, these Gephi and GraphViz. And just a second, let me show you something. It does not have a proper guide like Network X. Okay, still, I would suggest you guys first try it, then we'll discuss it, okay? And so, see, this is graphics layout. If I open it, I can pass program this layout. What layout do we want? Okay, and these are the layouts. So, see, let me just create it. Okay, one graphics visualization I will show. So what happens is when you will try Gephi now, you will find a lot of visualizations there. Apart from whatever Network X provides us, you will find a lot of visualizations there. Next does not have graphics layout. Okay. There's a wrapper for that. There's also a library for that. We need to install it. Pip install pygraphviz. Okay, so still this has this we are facing some error here. What I will do is next time we'll visualize, we will see Gephi, we will see GraphViz on my local system apart instead of Colab, okay? And so yeah, let's try this later on. I need to set it up. Or with the best solution to see how the graphs are visualized, you can simply search on Stack Overflow. There are multiple ways. This is Spring layout is there. See this they can draw. They are drawing color nodes with different colors, edges with different colors. The edges thickness can be different. The length of thickness can be different. Anything. So search for these things. Play around these things. And this is all about the layout stuff. Okay. These are some of the basic layouts. This read dot. This stuff. I would simply seriously suggest you try GraphViz library. Then yeah, we have studied shell layout, we have studied spectral layout, spiral layout. Did we see spiral layout? No, na. Let's try out spiral layout as well. Bipartite layout, bipartite. Actually, okay. So I asked for some books. Shriram, I will share the books. What books do you want? Hello, Shriram? Jaden. Yeah, sorry, just I'm addressing Shriram's doubt. So there's graph representation learning by McGill University professor. Representation learning. Something, yeah, this one. I will share the link here. Let me check if it's that one. Yeah, this is William L. Hamilton book. This is very basic GNN book, and I suggest every one of you, please read this introduction, chapter 1 and chapter 2. Okay, these things will come on later in the course, but I suggest you study chapter 1 and chapter 2. And Sriram, you have to study everything, so there's no other option for you. But everyone else, please study chapter 1 and 2 of this book. Chapter 1 and 2, yeah. This very basic book, Sriram, and apart from that, I suggest you email me personally on my email ID. Okay, please note it down. Email me personally. I will share other content with you as well. And if anybody wants about GNN, they want to study GNNs and they want advanced material apart from the material which is being taught in the course, please email me here. Okay. So somebody else, Manjula, yeah. Possible to view a live Google Meet members in a graph? No, I don't think so. There are softwares to do that. I don't think so. These things are possible right now. Basically, because these Google Meet and this stuff, this is proprietary. I don't think so. There are softwares to live Google Meet members in a graph. I don't think so. There's a software. And how would you see the difference between the people? Like, they are just members. They are existing in a meeting, and the data is gone. After the meet ends, the data is gone. I don't think so. Google. I don't know whether the Google is storing the data or not. But say the 10 members are joining a meet one, then 20 members are joining meet two, and we can see, yeah, these 5 members have joined both the meetings. We can connect them, but I don't think so. That is relevant. Anyhow. Okay, let's get back to spiral. Did we discuss spiral layout? No, no? Yeah, let's discuss spiral layout. We are discussing very basics, okay? I'm extremely sorry I have not Gephi installed right now, otherwise I would have shown you. And I seriously suggest you, see, beautiful. The nodes, they are arranged in spiral manner based on their label. See, based on their labels, based on the adjacency matrix. So in the adjacency matrix, the labels would be starting from 0 as only. So this is spiral layout, and this does not give us anything again. So these visualizations are very good until unless, see, graph visualizations are not about how you can visualize the data. It's about how you can present the data to other people. Okay? So you have to basically tweak with these parameters, these parameters, dimension, center, resolution, equidistant, blah blah blah, to make this visualization beautiful so that others can differentiate, others can understand. And for that, I suggest you try Gephi. Okay, Gephi. So basic idea is to first experiment on Gephi. Then either you can download that layout or use those parameters on NetworkX visualizations. Got it? Spectral layout you have tried. Multipartite. I don't think so. We need it in this case, but let's see. Okay. Linear graph, random layout, rescale layout. Rescale layout basically scales the graph between some axis. So that is not relevant, and that is. And BFS layout, yeah. So we'll try this as well. Okay, just remind me. We'll try this as well. First of all, apart from that, we have tried everything, right? Let's try multipartite layout. Complete multipartite graph, multipartite layout. And I don't think so that is relevant in our case, but still let's try it and see what we can get out of it. Error. So error, why do we have an error? Because this graph is not multipartite. Multipartite graph has some other properties. Let's try this thing. Okay, it's not printing. Yeah, every graph is that is why I said no. I don't think so. This makes any sense. This layout makes any sense here. Let me draw it. Simply let me draw it. This thing. What do we have here? Nothing. It makes no sense. See, so that's the problem with visualizations. They are default settings. They don't make any sense based on the data we give them. We have to tweak these data. We have to tweak these settings in some visualization software, and then we can draw the graph. Okay. We have BFS layouts. BFS layout is actually good. Let me show you. So BFS layout helps in a lot of cases. Let me show. BFS layout. So we will start the BFS from node 0. BFS is breadth first search. So node 0, we will visit all the neighbors of node 0, then we will visit all the neighbors of node 0. So in that manner we will draw BFS layout. Okay. Actually, wait a second. I think we will change the graph. Let me reload this Karate Club graph and check. Yeah, let's draw it again. See, node 0 has these neighbors, then these neighbors have these neighbors, and these neighbors have these neighbors. So this is basically breadth first search layout. Okay. Why am I using GPU? What's the last time I experimented? Okay. So yeah, that's all about basic visualizations. If you guys want, let me. Okay, wait a second. Let me install it. Do you know how to install? Like, let me show you on Mac. Mac OS Intel is there. It's not for Silicon. It's there for Silicon. Okay. Let's download and install it. Let me check. The installation works if we can see some of the basic functionalities of Gephi, because it has been a long time since I have used Gephi. Okay, so say this graph is there, this powergrid.gml. It has 4941 nodes, it has 6594 edges. I will open it, and this is the visualization you can see. Very random. Okay. Now let me change the color of the nodes. Okay, so what I do is here, you can see my screen, right? Screen is visible, right? Hello? Hello, hello. Yes, cool. So this graph is drawn in a circular manner, square manner, and we cannot see anything. So what I'll do is I'll select this graph. I will go here, I will select the color, I will change the color of the nodes to something, say red. Can I change the color of the nodes? Just a second. I think I have used very big graph. Can I change the color of edges? So okay, let's see. So I showed you this thing, random layout. Okay, then I have showed the rotation, but NetworkX does not give us these many layouts. Refan, who, okay, open or don't overlap, no overlap, contraction, expansion. If I simply apply expansion and I keep on running it, it will expand the graph. If I run contraction, it's contracting. If I use force atlas, force atlas basically performs force layout based on these parameters, and if I change these parameters, I can change these parameters as well. So see, something magical is happening, and we will see contractions happening because the springs are working. Okay, the nodes with high centrality, high degrees are going inside. The nodes with low degrees, they will be staying outside, and we will see something of, say, black hole type of thing. And we can change the iterations of everything from here as well. Okay, so how many times it's performed, everything we can change it. So repulsion strength is 200, attraction strength is 10. These are all the factors of a spring. Okay, of not a spring, basically of, say, magnetic fields. So instead of springs in force atlas, we use magnetic field sort of thing. In spring layout, we use spring sort of thing. let me stop it. Otherwise it will keep on running. So see, something happened. Okay. Let me show you how to change color and everything. So what I'll do is I'll select the graph. What happened? Select. I will go to data laboratory. No. Preview mode. Okay, yeah. Preview mode is here. Where's the graph? Where's the graph? Where's the graph? Default. Preview. Yeah, here's the graph. Okay. So about changing color and everything, nodes. We come to nodes here. Okay. Node labels are here. Where's the node color? Where's the node color? Color. I mean, I don't know. I too need to check out these things. I will share a tutorial, and no, you all can experiment on this. Okay. So this is force layout. Then we choose force layout 2. Force layout 2 comes up with other parameters, and see, something is happening. So force layout 2 has repulsion. It basically works on repulsion instead of attraction and repulsion both combined. So it's basically throwing everything away, and then based on the degree and everything, it will try to bring the nodes closer. Are you guys able to see it? Any ish? Yeah, smaller graph better, but now we have loaded it and we don't have time. And I will download a simple graph next time. Okay. So see, Force Atlas has done this. Let's try first make it random. Okay, let me make it. Sorry, I didn't apply it last time. The color and everything. Okay, I didn't apply it. Let me apply it again. Okay, wait. Okay, let me expand it. Acha, see, my bad. So we colored the edges green. We go to nodes. We change the node color to say red. We apply it. Nodes are red. Now we try this Fritterman rain gold graph. It's basically, as you can see, it's given. It basically acts based on the gravity of the nodes. So the gravity of each node is allotted based on the degree of that node. Okay. So it is very slow, like speed. Let me change the speed to 5 or something. 15. It's fine. See, at the speed of 15, the repulsions, the attractions, they are happening very fast, and it will expand very fast. Okay, label adjust no overlap. If I run no overlap, and no overlap is basically on this much big graph, it's not feasible to draw no overlap. Then we have open ORD, and open ORD basically starts from this thing, and then it expands. It keeps on expanding, and you will see. Wait a second. See. Yeah. You will see something beautiful. Edges. Let me change the color to something else. Blue. Yeah. Okay. Then we have Yifanhu. Yifanhu is very good visualization. Let's see. If I keep on running it again and again. So I suggest you guys study these graphs. Okay. I will not teach them because the theory behind them is not relevant to the course, but yeah, this is very interesting. These visualizations, Yifanhu, proportional. Okay, let me just make it random first. Now let me expand it. Okay, now let me run Yifanhu proportional. Wow. Is that a tool? Yes, it's a tool. See, so these visualizations mean nothing right now because we have a lot of nodes, but lot of nodes they do not need to be visualized. Smaller graphs, that's what we visualize. So let me check if we have a smaller graph or something. Close project, do not save, open. project. Import. Okay, just a second. Let me reopen it. Not save. Let's see which one is US airports. I think this should be small. Yeah, this should be small. See, these are big nodes as they have made the graph as per the Gephi format. So these big nodes may be some international airports or say the nodes, the airports with high connectivity to other airports. So let's do Yifanhu proportional first. And see, the nodes with lowest degree are going on the corners. Is the visualization clear right now? Is it clear? Yeah. The nodes with highest degree are in center. So this gives us, let's do Yifanhu, simple Yifanhu. Sorry, let me do random first, okay? Random. Sorry, random. Then let me expand. So whenever you want to run an experiment, I would suggest you do random first so that it makes it random. And then let's do this Fisherman pin gold. See the beauty of it. Okay, so based on the gravity it has put the nodes. Still putting it. Let me stop it. If I do force atlas, see. Just wait and visualize it, okay? Just wait. Since these nodes are very big now, so we cannot see what's happening behind. Okay, let me stop it. Let's try force atlas. Or say open org. So yeah, like we have to reduce the size of these nodes, and they have basically this network Gephi people have put the property of node size in this, so that's why I'm not able to visualize that. But if I do Fisherman Gold, you can see visualizations of based on the degree and the weight the node carries, each node carries. If a node has high weight and low degree, it's still existing in center. See, this has high degree but low weight. These have high weights and high degrees, that's why they're in center. This is high weight and high degree, that's why it's in center. Okay. Then we have Yifanhu. Let's run Yifanhu. So Yifanhu basically separates the nodes, separates the high degree, low degree nodes. This has like very basic parameter setup are there. So yeah, that's all I guess. That's all about Gephi tool. Any doubts? Which graph? This is US airport graph. It's default graph. This graph is a default graph inside Gephi tool. So any doubts till now? Pattern of exam. Let me check. I think their pattern will be somewhere around 45 to 50 questions will be there. There will be the most of the paper will be MCQ based and fill in the blank. Basically, one word or two words, something like that. Not and a few questions will be computation based questions. Like say five or six questions or 10 questions at math. They will be computation based questions. Apart from that, most of the exam will be simple, like theoretical based. It won't be very computation heavy. No coding in the exam. No coding, no Python package, no network X, nothing. Okay. Anything else? Numericals. I don't think so. The numericals have come yet in the paper. sorry, in the course, in chapters, okay, in PTL. But the best source I would suggest is their network. Just stay on screen. Social network analysis books. This one book for John Scott or someone. Let me check. I don't think so. This book contains numericals, but still, I would suggest go for this book. Okay, this is by Professor Tanmay Professor Tanmay only, and it has numericals. I have the book with me right now. Basically, I too have taken this course. I too have studied, and this is the only book. This is the only book which I have studied. You have Kindle, great. Kindle also works. Kindle, you guys can buy Kindle book. Kindle is very cheap as well, and numericals will not be that much hard in exam. They will be simple. Say the degrees. There, you have to compute the degree. You have to compute centrality measures. Based on centrality measures, what would be the node to be removed? What would be the node to be added? Like that, and what node to attack in case of centrality measure. These all stuff will be there. There won't be any very difficult numericals. Okay. So if you want to practice this is our best book right now because this is compatible to the course which we are studying. Other books I would suggest don't go for them because first of all they are of foreign authors. They are very expensive, so 3,000 4,000 rupees. Pirated copy if you can get. I would not suggest using pirated copies, but there is Kindle version is very cheap. Let me check. Social network analysis book. No, wait. Let me check. Amazon. Kindle version you can buy 500 600 something, and it you can also use Kindle on your phones and laptops, so that won't be an issue. You don't have to worry about buying Kindle to read the book. Okay. So yeah, that's all about the book. I don't think so. There are other books, and they are very the topic. The diversity is very like one book, and if you compare two books, the topics, the later on topics, in-depth discussion, they are very different. So you won't benefit from them because we are not studying those things in course maybe. So yeah, that's all. Any other questions? Manjula had some question. Manjula had some question back. YouTube comment something. Where is that question? Yeah, is it possible to identify the YouTube comment user node influencer detection? I didn't get your question. Can you explain it a bit? Manjula, you can unmute yourself and ask the question. Okay, so yeah, from next class onwards, we will be discussing assignments. We will be going in depth because this coding thing will be done by next class first 30 minutes. Okay, first 30 minutes I will be winding up this coding thing, and then we will experiment coding. We will do coding later when we will start GNNs. Okay, when we will start GNNs, we will do graph neural network. I got one deep learning on by yesterday and will also have Reed Hamilton. Yeah, yeah, that law. I would suggest you go for this author, this uh, researcher Michael Bronstein. I think you know him. I hope. Do you know him or not? He's an expert of this graph neural network area. He gave the basics of GNNs, and back in the day, he has a lot of work on geometrical deep learning as well, shape analysis. So I suggest you go through this author. I am pasting the link here. Go through the work of this author. And yeah, so what was the question? This is like it's possible to identify YouTube comment based on what comment user node influencer detection. I didn't get the question first of all. I suggest please you type it again. And I was saying about, yeah, so we will do torch, geometric, and this coding later when we will start GNNs. Okay, so torch, geometric, and this stuff you don't have to worry about right now. We will study that later. But I'm just telling the basic plan of the course, and that extra. I think we will get an extra lecture as well. Let me check with NPTEL. What is that Excel sheet? Sheets. So yeah, we will have 12 weeks plus one extra week. So I will take that extra week in between some other week, and we will squish that in between, and we will keep torch geometric lecture. 2 hours torch geometric, that will be very beneficial for those people who work in graph neural networks and who plan to work do research in GNNs. So yeah, we'll study those two things. But it will not be in this month. We will conduct it in September, mid-September somewhere, little September, like after 20th of September, somewhere. Okay, I'll talk to those NPTEL people. They will arrange the lecture for us. How many of you do graph neural network stuff apart from Chiram? Who's doing research in GNNs? Who wants to learn GNN? Yes. Mm-hmm. Okay. 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 There there are no tools for that, but I mean tools are there. Tools are there to visualize. So if you can make a graph out of YouTube comments, okay. So say a video is there. A video is there. It has 200 comments. There are sub comments. There are sub comments, and the video's views are affected. And say you can basically map the views of a video or likes based on likes and dislikes. But YouTube has disabled dislikes. So based on a comment of a user, uh, what happened? Yeah, based on the comment of a user, the people start. Am I audible? Okay. Based on the comments of a user, the people start disliking the video. Okay. So that has to be temporal in nature. So say at time t1, you made the graph. You see, yeah, so you perform text analysis on the comment. You saw that this is a negative comment, and you saw that like versus dislike ratio at that time. Then at time t2, you perform that task again. Okay. So first of all, this will be user specific. So first of all, you have to find the influential user. Influential user can be found based on the degree. This is very basic. This is a very basic thing which I'm telling. So what you can do is you can draw the graph of comment for a video, and you can find the influential user based on the likes on that user's comment. I don't think so. YouTube provides that. Mhm. I don't think so. YouTube provides that function to view the location of the users. I don't think so. Okay. Can you share those papers on my email ID, and in the next doubt session we will discuss them. Okay, 5-10 minutes we can take out and we can switch that idea what they are doing there, and I will try to explain clearly what they are doing and how you can do it. Okay. Okay. Sure. Great. Anything else, guys? You can stay. Like after 5 minutes, we will end the session. Okay, you can stay. We can talk. Okay. Anybody else who has any doubts? You're welcome. I don't think so. I need to ask one by one about doubts. You guys, please, if you have any doubts, basic to basic, anything works. Okay. These first two sessions were interesting for some people. They might have been boring for those people who already knew, or who already knew how to do those, who already know how to perform these things. Okay, how to search for a code. But I am doing this because some people are very new about in this area of GNNs, in this area of graph basically. They don't even know what tools are there, how to use those tools, how to use those libraries. So I'm doing that, these two sessions for those people. From next class onwards, we will stick very basics. We will stick to the course. We will stick whatever sir is teaching online, and we will study each and every part again. Okay. So if you have any doubts, please next class, I suggest you finish week 2 assignments. Okay. Those who are here, please finish week 2 assignments by next class, so that we will discuss week 1 assignment, as well as we will discuss week 2 concepts. Okay, in detail. Okay, whatever sir has taught, we will discuss in detail each and every topic. Apart from, if you have any doubts, okay, we'll discuss those doubts as well. We will solve some questions, not just questions. We will solve some real world questions. We will solve some case studies. Okay. So case studies say you have a degree thing, like you have studied degree centrality and blah blah blah. So what I will bring up a new example. I will show you how to search for case studies, how to basically learn a concept intuitively. So just a second, excuse me. How to learn a concept intuitively based on a real world example or something. Okay, so say later in the course we will study page rank and that stuff, and currently we have studied degree centrality, between the centrality, this stuff, and we will in week 3 I think we will be studying Barabasi Albert model and these models. So I will show you how you can basically understand, how apply that concept in real world and understand it more intuitively. So these things we'll study in next class. And for now, yeah, that is all. You all can drop. If you want, I need to discuss something with Sriram. Okay. Thanks a lot, guys. Bye bye. Just wait for a minute, Sriram. Okay.